Hello, everyone. I think we are live now from Berlin. Thank you very much for watching. We are going to be talking about from iterators to ranges, the upcoming revolution of the standard library. So to start, why do we want ranges? Let me see. Okay, here we go. So first of all, I'm sure quite a few of you have already tried ranges. Maybe some of you checked already the C++ upcoming standard for ranges and what they offer. Before C++20 ranges, there were other range libraries. There was Boost Range. Then Eric Niebler developed Range v3, which was actually for introducing it into the C++20 standard. And we also developed a range library. And we've been using a range library for quite a long time in our code. And I will be talking more about that. Let's first look at why you actually would like to use ranges. Well, I have here a piece of code. It's a vector, and you sort it with vector begin, vector end. And then you erase the duplicate parts of the vector with std unique, vec begin, vec end. And that's, let me see, I think I have to go to QA, so I see your questions. Let me go there. Okay, very good. I think I'll now see your questions. If you have any questions, feel free to ask. I'll see that once in a while, I'll look at that screen and find out whether you have any, and then I'll answer them as soon as I see them. Anyway, so so you have std sort, vec begin, vec end, and then you are removing duplicate elements with std unique, and this is just compacting the vector, and it returns the iterator until it actually compacted the vector. And then with erase, you can remove that duplicate tail. And as you can see in that piece of code, there's a whole lot of begin and end, and begin and end, and begin and end, and begin and end. And well, that's really ugly. So enter ranges. If you have ranges, you can write it like this. So you now say std sort of a vector, and you don't have to mention begin and end anymore. And then you just say vector erase, and there you would pass in whatever is std unique returning. Again, you don't need to mention begin and end, and you remove the tail. There you need to actually mention end, but and you can try this now in the range library, and it's on GitHub. If your C++20 implementation of the standard library doesn't have ranges already, and I think few of them have, but Eric Niebler has his implementation of the C++20 standard range library in GitHub, and you can try it out. Now, why do I think, or why do we think at ThinkCell we know something about ranges? As I already said, we have our own range library, and it evolved from Boost Range a long time ago, about 15 years ago. And by now, we have about 1 million lines of production code using it. And we kind of evolved the library and the production code together. And I think this is maybe the only way to get good libraries, is that they must see usage, and they must be used with a lot of code. And we have the additional advantage, because it's all in one company, that we can change the library and our program as much as we want, as much as we are willing to pay for. And we actually have people who do nothing else but refactoring the code and trying to find out better idioms and better ways to express the code with ranges. So we could try out all kinds of library designs and kind of narrow down on the good ones. And I think that was really crucial to make sure that we have a good library. And I will talk about the C++20 library. I will also talk about our library a little bit and how it differs from the C++20 library, and more importantly, why it differs. So let's talk about this piece of code again. We ended up with std sort vec, and then the erase, std unique, and vec end. There's actually a bug in this code, which is somewhat subtle, but it shows the advantages of ranges again. Std unique uses the equality operator to find out whether two elements are equal and thus can be removed. Now, vec erase or std sort actually uses the less operator. And if the less operator and the equality operator are not implemented in the same way, then, well, things break. You're saying, well, who does that? Maybe that's a stupid idea to implement them differently. But it's not really necessary to require the equality operator at all. If you are putting everything into one function, it's actually quite natural to say, okay, the std unique is something using something like greater equal, or the opposite actually of less, it's not less, to do the uniquing. And then all you really need is a single function that takes the whatever less of predicate you want to use, and you will use the same less predicate for sorting and then for the subsequent uniquing. And I think that's the way it should be done. We actually had bugs introduced by that problem, and we fixed them by putting these two operations into one, and so we could use always the same predicate. All right. Now, let's talk about ranges in a bit more detail. What are ranges? So ranges, first of all, are all the containers we all know. So this is a vector or a string or a list. They own their elements. They have a deep copy. So when you copy the container, all the elements are copied as well. And they have deep constness. So if you have a vector or a container in general that is const, you cannot mutate the elements. Now, there are a different kind of ranges, which the standard calls views. And these views are, well, they're quite different from containers. They reference their elements. They don't own them. When you copy them, you only get a shallow copy. And the reference is, or the copying of that reference is supposed to be O of 1. So it's a very lightweight thing, this view. And it has shallow constness. So even if the object is const, then still you may be able to mutate the elements. These semantics are actually quite common. They are exactly the semantics of iterators. And one of the simplest views is the view that simply aggregates two iterators. I've written it here as subrange, so it just has two iterators, and when you ask it for begin, it passes out the begin iterator, and if you ask it for end, it passes out the end iterator. Now, this solves some of the problems that we would like to solve, but probably can do a little more with ranges. And one of the more interesting applications are adapters and range adapters. So which problem do they solve? Let's say you have a vector of ints, and you want to find an element in that vector. So that's easy, right? You use range as find, and then you can pass the vector and the element you are looking for, and you get the iterator back to that element. Now let's say these integers that you are looking for are embedded in a data structure. So I have a structure A that has an ID and some data, and you have a vector of them. And now you're finding again a value 4, but this time that value 4 is in the ID field. Now, you could write it like this with find if. It's a bit ugly because you are really confusing how you are comparing, which is the equality, with the projection to the ID field. So then that's what I've done here. It's quite similar in semantics, really, to finding 4s in a vector of ints. I mean, just the int is in a different place. But you kind of can't see that anymore. And that's a bit ugly. We would like to have something that's a bit more elegant. So enter the transform adapter. A transform adapter essentially is transforming every element of a source range into some other element. It's doing a projection or a transformation for each of these elements. This transformation doesn't happen immediately when you are applying this transform, but instead it's applied when you are iterating over the range. So it's happening lazily. So down here you have the range as find, and then the and this pipe operator, that's C++20 syntax, and you pipe it into this transform that does a projection onto the ID field of A. And once you've done that projection, then you semantically have a range of ints, and then you can look for the 4 in the range of ints. Now, that's all fine and good. What is the iterator pointing to that you get back? Well, I mean, you've been looking in a range of ints, so the iterator pointing to int, right? Quite frequently, you may not want that 4. I mean, you know it's 4 because that's what you were looking for, but you were interested in the underlying A, in the source A where the int came from, and there is a function to do that. You can just call .base, and this base will go from the transform iterator, from the iterator that spits out ints, to the underlying iterator that is pointing to A. Okay, that's pretty cool. Now, except, and here we start with C++20 versus our library. It doesn't work because it doesn't compile. Now, why doesn't it compile? Well, the problem is the following. You have the vector, and you pipe the vector into a transform, and what you get back is some range object. And this range object will go out of scope when the range find is done, when you reach the semicolon. It's a temporary, and the temporary will be removed from the stack, and then it's gone. So the iterator is actually that you get back is pointing at a temporary. And C++20 is very afraid of you forgetting that, and thus it disallows these dangling iterators. Now, calling .base on them is quite frequent, though. So we do allow it, because in this case, there's no dangling iterator, right? So we take the iterator, and while that range is still alive, we just call .base on it. And then all we need is really the vector, because we have an iterator on that vector now, and no longer an iterator on the range object. So we do allow it. We say you can simply call .base, and the syntax up there with find tc return element we'll get to later. That's what we're doing there. Okay, before that, let's look at the implementation of the transform adapter. So how would you implement such a thing? The easiest way would be inside the iterator to just store the transformation function and the underlying iterator. And as soon as you are calling the operator star, so you're dereferencing that iterator, then the underlying iterator is dereferenced, and the result is passed to the transformation function, and the result is returned. So far, so good. When you call .base, you can simply pass out your underlying iterator that you remembered. So that's easy enough as well. All right. Let's look at another adapter. That's the filter adapter. And it solves the problem of, well, what if you don't want a single A where ID is 4, but you want all of them? So you want to filter your vector for all the A's where your ID is 4. And you may not want to do this eagerly. You want to do this lazily. You want to do it just as much as you have to solve your problem. So again, you have a vector, you pass it into a filter, and you get an object back that encapsulates that vector, remembers that vector, and also the filter. And as soon as you start iterating over it, as soon as you start getting the begin iterator and calling increments on the iterator and dereferences, you will actually iterate over a filtered view on that vector, only of the elements that pass the filter predicate. How is that implemented? Well, quite similar to the transform. There is a little bit of a problem, an additional problem here, which is that when you are incrementing this iterator, every time you're incrementing, you have to skip the elements that don't pass your predicate. So when you do that, it may very well happen that you were at the last element of your range. And when you just keep incrementing until your predicate passes, then you just will iterate over the end of your underlying range of your vector in that case. And that would be bad. So every time we are incrementing, you can increment once safely, that's okay. But then we actually have to check whether we have fallen already off the end. And if we are basically at the end of our underlying sequence, underlying range, then we have to stop. And for that, we need the end iterator. So the iterator needs to store the iterator, the end iterator, so the iterator, the underlying end iterator, and the functor. Okay. How does this kind of filter look like? So you have a filter of a filter of a filter of a filter of a filter. When you now look at the iterator of this guy, how does it look like? Something like this. So every time you are creating another layer in this filter, you again have to store two iterators. And these two iterators, each of them store, again, their functor, and again, two underlying iterators. So you get nice and exponential growth of the size of the iterators. And if you have 10 layers, then you easily have 4 kilobytes of sized iterators moving around your code with where you write your for loops with. That is certainly less than ideal. So we have to solve this problem. Now, the idea is, of course, iterators must be kept small. Otherwise, there's really no point of having them. The idea is, let the adapter object, the thing that you generate when you invoke the pipe operator, where you pipe the vector into your filter or transform, let that object carry around all that is common for all the iterators. And then all the iterators can just carry a reference to the adapter object, or a pointer, and the underlying iterator, the base iterator. And thus, they can be nice and small. Okay, so that's what currently C++20 does. That's state of the art. And this is also the reason that C++20 iterators cannot outlive the range. So you need to keep the range alive to use the iterators. You can't just have the range die and keep using the iterators, because then this pointer that's inside the iterators will dangle, and that won't work. So how does now the filter look like if we use this optimization? So we have a filter of a filter of a filter of a filter. And then you get this. You get the pointer to the underlying range and an iterator. Well, why the static bool? Why the static cast bool? Let's go back. I got a question. Why is there a static cast bool? The static cast bool. I have to defer this question. I'll get back to you. Okay. We were here at with the filters and the functor. As we said, it's still not great, because every iterator still is carrying around a pointer to the underlying range and another iterator. But the iterator itself, this underlying iterator, may again carry around a pointer to its range and an underlying iterator. So you still get linear growth. If you have 10 levels, you still have maybe something like 40 bytes or 80 bytes of iterator size, which again is not great. Now, enter the index concept. So we try to do better than C++20. This problem kind of bugged us and said we want to use you want to use ranges everywhere, and so we want to be more efficient. Now, what's an index? Well, the idea is really quite simple. The index is just like an iterator, but in order to run operations on it, you need to provide not only the index, but also the underlying range. So here you could, for example, implement these index operations on the range itself. You could say, okay, there's a begin index, end index, but then there is an increment index, and that increments the index you pass to it. But this pointer here is the index range. So you need the index range and the index in order to increment the index. And the same for all the other operations. Now, why does this help us? First of all, let's think about if we are introducing these indices. Of course, the whole world is not going to stop using iterators. This is just not going to work, right? So the what we need to do is, in order to make this feasible, is to provide some sort of compatibility with existing iterator code. So you should still be able to use iterators. How will that work? Well, if you have an iterator and you want an index, that's quite simple, because the iterator can do anything that the index does. It just doesn't need the range. So if you provide a range, well, you can simply forget about it, just use the iterator operations instead. So that's simple. The iterator from index, the other way around, if you have an index and you want an iterator, that's only marginally more difficult, because all we really need to do is we need to package the pointer to the underlying range with the iterator and the index. And then we can write, like, for example, the operator plus plus by invoking range together with the index, call the operation on the range, and that's it. Okay, so that's quite simple. So if we have an index, we can easily turn it into an iterator. Now, how does that help us with implementing nice and efficient filters, for example? Well, here's an example for the increment index of the filter. If you now do increment index for a filter view, you increment the index, and when you have to check for the end, you don't need to carry around the end iterator. You can actually take it from your base, because it knows, the filter view knows it's actually base range, and it can actually get the end index from there. So it asks the base for the end index and stop falling off the end. And then again, you dereference and you call your filter predicate. Okay. So let's see why this is now efficient. You can see here that the index that we are getting into the filter is the same index as used by the base range. So I'm passing mbase increment index. The index that I'm passing in there is the same index that I can use. I don't need any extra information in my index. And conceptually, it's simply just the position where I am in the underlying range. And that's all I really need. So if you now stack all these things, then this will just remain the same. It will just, the index of a long stack will still be the index of the underlying range, at least for most adapters. For the transform adapter, the filter adapter, it's certainly true. So you can stack them in any way you want, and you will still have an unchanged size of the filter, of the index. So when you then stack all of them and get an iterator from this whole stack, this iterator will again be just a pointer to the outermost range and the index, which is still small. So essentially, you're getting all the iterators from this deep stack are only going to have 2 pointers, no more ever. All right, here's another problem with C++20 ranges. Now, if the adapter input is an L-value container, then so you're passing in an L value into your filter. Then the filter, as we said, will create a view. It's a lightweight object that is just holding a reference to that L value container. And so you get all of one copy and shallow constants and so on. Okay, so this is the example. You create a vector and you pipe it into the filter. Now, what if you are passing in an R value? Create a vector, and you pass it directly into the filter without giving it a name, without having it in a variable. Now, this would create, as soon as that line is completes, it would actually create a dangling reference, because the filter would try to point at a vector that is long gone out of scope. Now, C++20, similar to the dangling iterators, tries to save you from these mishaps, and it just doesn't compile. So all these filters require you to pass in an L-value container unless it just says this doesn't work, which is kind of unfortunate. Say you have a problem like this, where you have a vector, you're trying to return a lazily filtered container. So this is not so obscure, really. You have you internally in a function, you create a container, and you want to lazily filter it before you pass it back out. Of course, you can do it eagerly, but maybe that's not necessary. You just want to leave it to the caller how much he wants to consume it, and then he maybe just deallocates the memory and the whole vector is gone. So and you save a lot of time by not going over it and eagerly filtering it. So what could you do? Well, it's actually difficult. So you're creating a vector here, and then you're saying, okay, I'm going to make a tuple of this vector and a filtered version of this vector. Well, this would actually compile, but it wouldn't work because of the vector that you pass to the filter is still the vector that you had on the stack. It's not the vector in the tuple. And to kind of create the tuple in a way that it holds the vector and a filter that's pointing to this vector, and then you are possibly copying the tuple around, and then again the reference is out of scope, and it's a mess. So I cannot think of a solution to this problem, an elegant solution to this problem at least. How to solve it? I mean, maybe you could store it on the heap or something. It's ugly. It's difficult. So we came up with a solution. Okay, which solution do we come up with? So when we are filtering an L value, you really want to do the same thing that the C++ standard does, right? So you want to hold a reference to your vector. That's fine. But if the vector is, or if your container is an R value, then I think it is a good idea to just, if the filter just automatically says, okay, I have to keep that vector around, so I'm going to move it into myself, and so that I always have this value. It's a bit philosophically maybe a little bit ugly that suddenly this filter is no longer a view. And I think this is what kept them in the standard from actually adopting this solution. The filter is now suddenly a container. It carries around values. And when you're copying it, it would actually copy all the elements with it. In practice, this is really not a problem. We found this to be very convenient, and we haven't found any places where it would surprise us that this copy would actually create a real copy. In practice, you don't copy ranges much. What you're usually doing is, just like a container, you don't copy a vector much. If you copy them, you usually would evaluate your range. You don't take it as it is. You just copy it into a vector, say. You evaluate what you need, and then you carry on with the values that you got. I mean, if you're allocating memory anyway, then you probably want to allocate only the memory that you need and no more, and you want to do it in the form that you want. So the filter, again, is even in the scenario where you have where you have an R value container, is always lazy, which I think is quite important, because if you it's important to make sure that the laziness in the library, that the laziness and the containerness are really two orthogonal concepts, that you don't have the absolute requirement that whenever you want to turn something into a container, because you have to keep it alive, that at that point already you have to do your operation eagerly, because this is different from copying, right? I mean, usually you're just doing a move. So moving a vector is actually quite efficient and is really not a problem at all. So this lets you keep these two concepts entirely orthogonal. Now, the alternative would be, or in C++20, I think programmers would be very much enticed to do the operation eagerly, which you don't really want to do. You want to keep these two concepts orthogonal. Okay, let's talk about more flexible algorithm returns. So we have range algorithms, like this find here, and it returns an iterator. And I mean, quite frequently, when you are writing such a function, you know, for example, that you don't want an end, You know that you want an element, you want to find something, otherwise your program is ill-defined. How could you solve this problem? Well, here we actually have a template parameter that describes what you are getting back. So it gets passed it gets called with the iterator that results. And if you found something, and if you didn't find something, it says, okay, pack some sort of singleton for me. Pick something that you want to have returned if I didn't find anything. So in one case, you can basically do whatever you want with the iterator and return that. In the other case is, well, here's the range, but I didn't find anything. Now you can again do anything you want. And the default thing would just be, okay, if you pack the iterator, you just return the iterator. If you pack a singleton, you return the end of the range. Okay, and that's return element or end. Now, very frequently, you may not want that the end is returned. You may say, okay, the end cannot be returned because I know that I should find an element. And very frequently, you scatter your code with iterator unequal end, iterator unequal end asserts that are ugly and are not very expressive. Instead, you could just say, well, return me an element. And if you cannot return me an element, then just assert. And you can do this with a simple change in this return structure. And this is actually stolen from Boost, I should say. Boost had a very similar facility, and we extended it a little bit. Now, there's another nice thing you can do with this. You can introduce a little wrapper to an iterator, which, well, for pointers in particular, it basically just says, if you don't want to pack anything, then I just give you a null pointer back. And if you don't, if it's not a pointer, if it's a regular iterator, it just wraps the iterator, it's kind of in an optional, and says, if the iterator is nothing, then if I bool cast this iterator, it says false. And then instead of writing iterator something equals blah, 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 and then if the iterator is not end, you can simply write if auto it equals find, and then return element or null. So in one line, you basically express that you want to find something, and if you found it, then you do something. This is a whole lot more convenient than always having to pull out the end. Okay, what else can we do with ranges? Something, and I'm coming, well, not quite to the end, but here is one of the things that we did that are furthest from what conventional iterators or ranges do, which are generator ranges. So if you have a function that just traverses things, essentially a visitor pattern, you get a function, and then if you have some window, then you traverse that window, and then you found a button in a list box, and then you found another window, and you traverse that recursively. So you're traversing some tree, and this really kind of behaves like a range, right? Because it's a sequence of things, but it doesn't have any iterators. And wouldn't it be nice if we could use iterator functions on these kind of objects? Well, let's try that. So it would look like this. So we have an anyOf. The anyOf is a function that just takes a func and traverses widgets. So it's basically taking a sync, a callback, and calls that callback with all the values it has. And what then happens is that these elements are just piped into the second lambda here, which takes widgets, and it does something with it. And so essentially, a range is suddenly any lambda or any object that supports the operator parentheses, the function call operator, taking a sync. So anything that takes a sync is now a range. And anyOf works with it just fine. Now let's see what we are really doing here. Usually with normal iterators, we do external iteration. That means that the consumer of data is calling, before I do this, let me go through 37. Someone asked me a question. Why doesn't it compile? Okay, it doesn't compile because they don't want you to compile it. They don't want it to compile. And they don't want it to compile because the the views, so technically it's done by, it's an R value. Create vector creates an R value, and if you pass an R value into a views filter, it doesn't compile. The reason is that R value would go away when the statement finishes, and then filter would contain a dangling reference. And they want to protect you from that. And that's why they say, no, you just make this not compile. Okay, I hope this answers the question. So let's go back to the generators. We do external iteration. In external iteration, the consumer calls the producer to get a new element. And C++ iterators are examples for external iteration. So whenever you want an element, you call star it, and then you call plus plus it, and then you call star it again, and you call plus plus it. And the consumer in this point, in this example, is at the bottom of the stack. So for iterators, so it is the one that's calling into the producer to get an element. No, they're not. They're part of the ThinkSize library, not the standard library. I have a question whether the return element or end is going to be part of the standard library. Unfortunately, not. So that's us. So consumer is at the bottom of the stack, producer is at the top of the stack. Why? What is good or what is bad about it? If the consumer is at the bottom of the stack, it can actually run a contiguous code path for the whole range, right? Because it just, whenever it needs data, it just calls in and gets the data. That makes it easier to write. And you also get better performance because essentially your state that your algorithm in is encoded in an instruction pointer. You can just write a regular algorithm. It's not chopped into portions, and every time a portion is called, you need to again find out where you are. And you have no limit for stack memory. You can use any amount of memory on the stack efficiently while you're doing the whole iteration. The producer, on the other hand, in case of iterators, is at the top of the stack. So it has a contiguous code path only for each item. Every time you deliver an item, you get interrupted, and I will call you again for the next item. Makes the producer harder to write, and it has worse performance because it only has a single entry point, and every time you call the producer, it has to find out, okay, where am I in my iteration? And you can imagine if you write an iterator for a recursive data structure, this is actually quite an issue. So it's much easier to do this when you're at the bottom of the stack and you can simply recurse into your tree. And you only have a fixed amount of memory that you can remember between calls. Within a call, of course, you can use the stack, but between calls, you only have a fixed amount of memory, or you have to allocate heap memory. Now, the opposite of external iteration is internal iteration. So it's just the other way around. Whenever the producer has an element, it actually calls a function of the consumer. So it's iterator, it's visitor pattern. And many enumeration functions, maybe in the operating system or somewhere else. Here I have a Windows, enum threat Windows is a Windows operating system function, API function. So many of them are written like that, where you get offered these elements one by one. In this case, the producer is at the bottom of the stack and has all the advantages of being at the bottom of the stack. And the consumer is at the top of the stack and has all the disadvantages of being top of stack. So far in C++, you don't have much of a choice. Iterators are external iteration, not internal iteration. Before we explore what we want to do, let's talk about coroutines, because it gives the opportunity, they give the opportunity for both the consumer and the producer to be semantically at the bottom of the stack. You are essentially writing a generator, and every time you're passing out an item, then the control flow changes to the other coroutine, and it keeps running until it again needs another item. So you basically have two parallel control flows, and you always change between one and the other whenever you have an item or you need a new item. Okay. Now they come in two flavors, these coroutines. One are called stackful. They have two stacks, and you switch between them. The problem is that they are quite expensive. Usually they are implemented as operating system fibers, so they actually need a real stack. So about 1 megabyte of virtual memory per coroutine, and that's certainly for an inner tight loop. That's not ideal. If you every time you're running this loop, you just have to allocate 1 megabyte of stack space. Now C++20 will get stackless coroutines. The problem here is with stackless coroutines that they are infectious. When you have a coroutine that is supposed to pass out an item, this has to be a coroutine. But if it calls a subroutine, if it calls a function that is also supposed to pass out items, it as well has to be written as a coroutine. So effectively, your whole call tree in this situation would have to be written as a coroutine, which is kind of not so nice. So you could imagine like how a standard library looks like, where for every for each, you have to have a version of the for each that is a coroutine. So it can actually support internal iteration. So, right. So this may not compile if traverse widgets is not itself a coroutine. Okay. That's a disadvantage. So it can, if you just have a regular function, it can only yield in the topmost function, or you have to make all the functions you call coroutines as well. They are still a bit expensive. So these resume points, when you pass between the coroutine and the consumer coroutine and the producer coroutine, these jumps are kind of like dynamic jumps. They are kind of like virtual function calls. So they have to save and restore some registers, and you cannot do aggressive inlining between them. At least it's difficult to optimize. So for the time being, for tight loops, it's probably better we stick to either internal or external iteration. And it turns out internal iteration is for many algorithms good enough. For find and binary search, you can't really use it because you need iterators. But for each, it's fine. For accumulate, it's fine. For all of, any of, none of, it's fine. So I think if you look into our code, most of the iterations now happen without iterators. Maybe the underlying iterators of the container, but if you on top build filters and transforms and so on, they can actually be written entirely as with internal iteration. So it's quite simple. When you're getting a value and you want to filter it, your underlying producer produces a value. You just look at that value and either reject it and say, well, I'm just going to return to the producer, or I'm passing it on to the consumer. So it's quite easy to write a filter that can deal with internal iteration. Same with transform. So we said, okay, why not allow ranges that support internal iteration? So then an any-of, for example, looks like this. So you have an any-of, and it takes a range, says, okay, the result is false, and now you iterate through all the elements in the range, and you take a Boolean, and that Boolean will be accumulated into the result, and then return the result. Okay. So and for each in this case is actually the common interface for the iterator index ranges or generator ranges. It works with all of them and does the right thing. I mean, for each is just fine with internal iteration. It's actually just kind of turning external iteration into internal iteration because it calls its body with one element one after the other. Now, is this okay as an implementation of any-of? No, it's not, because the ranges any-of, of course, must stop when you encounter true. So how do we do that? Well, first idea was we just throw an exception. Unfortunately, that's not a very good idea because it's way too slow that every iteration that gets interrupted is throwing an exception. So we needed something else. And we came up with an enum, which is break or continue. And so if your sync in this case is, or if syncs in general are returning break, then the outer range is supposed to stop iterating. It's supposed to stop providing values. And we've implemented that throughout the whole library. So now there is there's something where this you may consider this a bit inefficient, right? Because you have to return break or continue, and quite often you probably have cases where your sync would always return continue. You never want to break. And fortunately, you can actually elide the check. If the functor returns break or continue, then you just check for the break. But if the functor returns nothing, for example, or anything else, then there's really nothing to check. And at compile time, you can just elide the check. So it's efficient, it's fine. Interestingly, you can actually write more efficient ranges, iterator ranges, if you restrict yourself to internal iteration. So let's look at concat and how to implement it as a range. So you have a concat is just concatenates all the ranges that you pass to it. You have a list and you have a vector, both are of type int. That's all good, and you concatenate them all. And then you want to get the contents of the list followed by the contents of the vector. So how would you implement that? Well, the ranges that are passed through this concatenation, are not necessarily of the same type. So you have two different indices, index types, and you have two references to ranges. And the actual index is now a variant between the two index types. If you are still with your iteration inside range 1, then your current index is of type index 1. If you are already inside the range 2, then you will have an index of type index 2. So you have to keep a variant of the two. Now, every time you increment, you actually have to switch kind of on your index type. You have to do a visit on your index type and say, okay, if I am still at index 1, then I increment it. It could be that I'm reaching the end of range 1, and then I'm switching to range 2. So I'm reassigning my variant to the type index 2. And if I'm already on index 2, then I can just simply increment. So that means that for every increment, you actually need to branch. You need to make a decision that every time you're getting called, this iterator plus plus or plus plus iterator is called on the concatenation range, then it has to decide, okay, which range am I in? You need a branch. And that costs performance. The dereference is quite similar. So here also you have to decide, okay, am I on the first in the first index, or in the first range, or am I in the second range? And then you have to call the dereference on the first index or the second index. And is there a way to avoid all these branches? Let's see if we can do that with generator ranges. So the concatenation would implement, in addition to its iterator interface, which stays as it is, because you may need iterators at some point, it also implements a generator interface, which is simply doing a for each of each one of the ranges. So it couldn't be any simpler. So what we've done here is we can basically, whenever we run an algorithm on a range, we can make a dynamic decision, a runtime decision, whether the algorithm that you're running actually requires iterators or is happy with internal iteration. And then you can use internal iteration. So that's also something we've implemented on our library. So, which brings me to the end of my talk. Now that we have all this range stuff, and here it is, so it's on GitHub, our range library, you can try it out. And if you don't want to try it out, try out the C++20 library. So certainly everything is much, much better than sticking to iterators. So this is certainly something that will change the way you're programming. And I hate the range-based for loop. Why? Well, the problem with a range-based for loop is it encourages people to write code like this with a for loop. And they could have written something like this, which is much more elegant. Thank you very much. And I think we have a few minutes for questions. Actually, at least the Clang compiler, the question is there a compiler that implements C++20 ranges? And at least the Clang compiler, I think also now the Visual Studio compiler, they will actually cleanly compile the Eric Niebler ranges. And this is an implementation of the C++20 ranges. So if you want to stick to the standard, you can take Eric Niebler's code and use it. So that's just fine. It works at least in Clang, I think GCC as well, and Visual Studio. I think Visual Studio a while ago, they prided themselves in compiling the range library cleanly. Someone is asking, in case of rvalue containers, if the range holds a container and you pass that range around, doesn't that make deep copies? Well, it would make deep copies if you would actually pass copies and you don't move or you don't pass by reference, which you would probably do. So as long as you're passing around references, and I mean, if you have normal containers, you are basically used to passing around references. So you would just treat these adapted containers just like any other range, just the same. You just pass them around by reference. It makes sense because usually you may not even know whether you're getting a container or a view. You may just get something, and in that case, it's actually it would make sense to say, okay, I'm always taking these ranges by reference, and then it really doesn't matter. So so in practice, this is really a problem because you're really not copying them. ThinkCell ranges library compiles on the standard compilers. It compiles on Visual Studio and it compiles on Clang. We haven't tried GCC. But I would be happy to actually to fix it for GCC. I think that shouldn't be a problem. Maybe it compiles right out of the box. So if someone is interested, just let me know. Oh, why the static cast bool? Yes, slide 25. Why the static cast bool? The reason there is that you want to make sure you invoke the explicit bool conversions. So when your predicate returns something which is not explicit bool convertible, then the static cast bool will force this conversion to bool, which is, since you are talking about a predicate, that's probably what you want. Yeah, so that was the question from slide 25. No, I don't. So there are questions regarding. So what standard does the ThinkCell ranges library require? We are usually compiling against the latest Visual Studio, so you will be fine with C++17. We don't use concepts right now, and so so you don't really need any emulation, and compile times versus ranges v3, I don't know because we haven't run one against the other, so I wouldn't know. But certainly compile times are important for us, so we try to optimize them. Will the standard ranges support const.expr? I don't know to what extent. We do it certainly as much as we can. So I don't know about the standard ranges. Will ThinkCell ranges and the standard ranges be merged? Well, I mean, they are compatible, and we will try to make our ranges as much compatible as possible with the standard ranges. So, for example, if you pass a standard range into a TC for each, ThinkCell for each, it will certainly work. If you pass it into the algorithms, it will certainly work because it's all based on iterators. So the ThinkCell ranges and the standard ranges are by and large interoperable. There are, of course, things which don't work with the standard ranges. Like if you pass a generator to a standard range algorithm, then it won't work. So as long as there's a begin and an end, then the standard algorithms will work. Okay, so there is the return element or end. Is the return element or end going to be part of the standard library? I answered this already. They are ThinkCell. They are ThinkCell specific. They are not part of the standard library. Standard library still returns iterators. What would be the worst thing you could do performance-wise in your library? Good question. We try to avoid we try to avoid these kind of pitfalls. There are a few things which are not which are difficult to optimize, and where C++20 and our library made different choices. One tricky thing is the begin of a filter range. We didn't do anything special, which means when you are running a begin on a filter range, the first thing it would do is it would iterate until it finds an element that is not filtered away. Now, if your algorithm, and maybe that brings me to what's not performance-wise bad. If you do a reverse adapter, which exists, you can have a reverse adapter on a filter range, then every time you are incrementing your iterator of the reverse, the underlying iterator gets decremented, and you need to check against begin. So then you would again and again query the begin of the filter range, and the standard library solves this problem by caching inside the filter object. It's caching the begin iterator, which works is more difficult when you actually aggregate, in our case, when you aggregate the container. And it has the disadvantage that you have to have, for a simple begin operation on a filter object in the standard library, the filter has to be mutable. So getting the begin iterator of a filter object mutates the filter object, which is surprising and is a bit weird. It has also consequences for multi-threading. Calling begin from multiple threads is a race, because it is a mutable operation and there is no lock aggregated into the filter object. It would be much too heavyweight. So you get a race when you call begin on multiple threads. That's quite an ugly corner case. It's which why we didn't fix it, and so far we haven't seen any case where it was really a problem. But it potentially it may be. And I don't think there is a really nice, elegant solution to this problem. You only have 55 commits in the GitHub range repo. We don't develop directly against the repo, so we actually have larger changes into and in our local implementation, and then we put out larger commits into the GitHub range. So we don't develop directly against it. For the reason that we are making many little changes, and we want to have a minimum of stability before we do another commit to the GitHub. And so the GitHub range is it terribly stable? Well, we do. I think it's stable as in terms of it has few bugs. The problem is more that we feel free to change it at any time. If I had a project, an external project, would I use it? I probably would, because it has so much stuff in there that you could always just get it, and even if you don't want to make an update, it's still a very good starting point for your own developments. If you update, then you have to do changes to your code, which is exactly the changes that we have to do to our code in order to make it work again. I would still think that the benefit would far outweigh the cost. And if it ever dies, or if it's no longer supported, which is I cannot really see that, but if that's a concern, then you can always keep developing it on your own. It certainly has lots of algorithms. It has lots of more stuff than just ranges. It has, I don't know, enum sets, for example, which are bit sets of enums. So you have an enum, and you want to generate basically a bit set that corresponds to the values of this enum. There's support for that, or there's there are just many little utilities that we use on every day, and you're quite free to make that public as soon as something needs it, something is convenient to make public, then we make it public. And someone asked again about compile times. I can't compare it to the standard library. I don't know, because I haven't tried the standard library. I haven't profiled the compile times. All right. I think we are 5 minutes over already. So I will be in the booth for a little while. So if someone has any more questions, then feel free to catch me there. Otherwise, thank you very much for listening, and hope to see you soon. Bye.